In this module, we're going to talk about the ACI logical model and the different logical objects that we configure in ACI, such as tenants and contexts, also known as VRFs or private networks. We'll talk about bridge domains and the subnets that reside in them. We'll talk about EPGs, endpoint groups, as well as application network profiles and contracts that govern the communication between those EPGs, as well as quality of service in ACI and how that's implemented. So the ACI logical model. So let's go over some terms real quick. First, we have the concept of the tenant. We've talked about this a little bit before. This is a logical separator, separates traffic, administrative duties, visibility. So in a multi-tenant environment, one of the things that you're required to be considered a multi-tenant environment is I need to be able to mask your view. I need to be able to hide what you can see. If you think about it, when you log into Gmail, you can't read other people's email. So Gmail is a multi-tenant environment. If you log into ACI, I can restrict. If you're an administrator, you can see everything. If you're an infrastructure administrator, you can see everything. But if you're logging in as Coke or Pepsi, then I can restrict what you can see. So tenancies in ACI can be used a multitude of ways. You can just create one tenant. That's fine. You can create a production tenant, a test tenant, a dev tenant, a QA tenant, etc. You can have different business units. You can have different project groups. You can have different organizations within your group. For example, you've got one group that maintains your next generation applications, another group that maintains your legacy applications. You can put them in different tenants. One thing that tenancy in networking is especially used for is shrinking the failure domain. So within a tenancy, you're restricted to configuring objects that you have been granted access to. So you don't have access to objects you don't have access to. So you can't misconfigure those objects. So we can use that to really shrink the failure domain so that if you have Coke and Pepsi and Coke screws something up, it is very unlikely that it's going to affect Pepsi and vice versa. So those are some things to think about in terms of tenancies. Next up, we have our layer 3 private network. Sometimes we'll refer to it as a private network or a VRF. It's a VRF Lite equivalent, provides separation of routing instances and administration. So you can have multiple VRFs in a given tenant. You need at least one in order to be able to pass traffic for a tenant. But you can have multiples. And then multiple tenants or multiple VRFs can have overlapping IP space because these are separate these are separate routing tables and routing domains. Bridge domain, it's a container for subnets. It is not a VLAN. And it can be used to define a layer 2 boundary though. We can have multiple VLANs assigned to a bridge domain. If you think about it, what we used to use private VLANs for, what we still use private VLANs for, that's kind of what we're going to be talking about with bridge domains. So that's one of the more interesting aspects of ACI that doesn't have quite an equivalent or an analog in the traditional networking world. So we'll spend quite a bit of time talking about bridge domains. Subnet, same thing as in traditional networking. It's an IP addresses within a given bridge domain. It must be unique within their associated L3 private network, but they can overlap between tenants and they can overlap between other VRFs in the same tenant. Next up, we have contracts. These represent policy decisions between EPGs. A contract is provided by one EPG and consumed by the other. And this is how we do how we pass traffic. If we have forwarding set to enforced in ACI, which is the default, then everything inside of an EPG can talk to each other unrestricted. So if I have multiple virtual machines or multiple hosts in a given EPG, they can talk to each other unrestricted. But everything outside of that EPG cannot talk in, and that EPG cannot talk out unless you explicitly provide a contract to allow to do so. There are ways to get around that if you have a more traditional networking environment and you don't know what ports you need to talk to. So there's ways we can deal with that. But by default, and that's what we're looking for. If you think about it from a security perspective, that's a much better security profile we want to be in. We want to be in whitelist networking rather than blacklist networking. We want to be explicit in what we allow what connections we allow through instead of being the opposite. And then finally, we have our endpoint groups. These are containers for objects requiring the same policy treatment. Oftentimes, an EPG is equated to a given port group in VMware. It can be equated to a VLAN, and sometimes even IP addresses if we do if we do microsegmentation. So those are different things we can do. So here's the overview here itself. We have our root or universe, sometimes called uni. We have our multiple tenants, tenant A, tenant B. A tenant can have multiple VRFs, and they can have overlapping IP space. Every tenant can have multiple bridge domains, and then each bridge domain can have multiple subnets. Kind of like if you have like an SVI in a traditional networking environment, go to VLAN 100 IP address 192.168.1.1 255.255.255.0, and then you can do a secondary one, and that would be something like that. So you can't put more than one subnet in a given bridge domain. And then we can have multiple EPGs that are connected to a given bridge domain. Another way to look at this, we'll look at the one-to-one, one-to-many relationships. So we can have on a given tenant, so this could be Coke or Pepsi or Kirk or Picard or whatever, we have multiple layer 2, layer 3 outside networks. So the N indicates that we can have many of these. We can have many application network profiles, but we have an EPG can only exist in a single ANP, in a single application network profile. But an application network profile can have many EPGs. Typically, if you have a 3-tier stack, then you're probably going to have 3 EPGs. You can have more, you can have less, kind of depends on your application. EPGs can only exist in one bridge domain, but a bridge domain can have multiple EPGs. And a subnet you can have multiple subnets in a given bridge domain. However, a subnet is restricted to a single bridge domain. So I can't have a subnet that is split between multiple subnets, unless it's in a different context. So if I have a bridge domain in one context and a bridge domain in a different context, then I can have the same subnet range in both bridge domains. However, they are not the same subnet because they are part of different VRFs, so they're considered a different network. We can have multiple contracts. We can have multiple contracts in between EPGs. We can reuse the same contract for multiple EPGs. We can have one contract that just says port 80, and we can use it all over the place. A contract can have multiple subjects, and a subject can have multiple filters. And the filters can exist in multiple subjects as well. So what is a tenant? A tenant is a logical container for application policies. We have a couple of pre-configured tenants. You can't get rid of them. We have the common. These are policies that can be accessed by all tenants. We have the infrastructure tenant. So that's the VXLAN overlay infrastructure configuration. It's a private L3 network. Private bridge domain does not leave the ACI fabric. We have the management for in-band and out-of-band management configuration of fabric nodes so we can access them. And perhaps they might need to interact with like NTP servers, or they should interact with NTP servers because you really should have NTP enabled. And then we can have like other tenants for T01, that's a user tenant. So creating a tenant is pretty easy. We just give it a name. Call it whatever you like. We can put in some tags to help identify different aspects. We can put security domains. If you create a security domain for a tenant and you assign a user to a security domain, that means they can only see their own tenant or whatever tenants you give them access to. We're going to have a VRF. We don't have to create a VRF when we create a tenant, but if we want to forward traffic, we're going to have to anyway, so you might as well just create one there. L3 private network VRF, also known as a context. Typically that's what we see it referred to as in ACI, or a VRF, but it's a layer 3 private network. Represents application policy domain and layer 3 forwarding. So one or more private networks are associated with the tenant. One or more bridge domains are related to a private network. Equivalent to a virtual routing and VRF instance, and IP addresses must be unique within the private network, but they can overlap outside. So Coke and Pepsi can use the same address space. If you have Coke and they have Coke and Diet Coke as two different VRFs, we can overlap IP space there as well. Doesn't necessarily mean it's a good idea, but it's possible. So when we create a VRF, the first thing we're going to do is pick our policy We're going to give it a name. We call it VRF1, or here we're just calling it corp. Policy enforcement control preference. If we pick enforce, that means that EPGs cannot talk to each other unless we implicitly allow it. If we do unenforced, then it's a free-for-all. Policy control enforcement decision. We're going to make our decisions on egress, or we can do or ingress rather by default, or we can do egress, but typically ingress is what we do. Endpoint retention policy, and we can pick a couple of other things as well. Then we can also create a bridge domain, configure BGP policies, OSPF policies, EIGR policies, etc. And we can configure that. So a bridge domain. A bridge domain is not a VLAN. A VLAN it's a layer. If you think about what a VLAN is, it's a LAN that has been virtualized so that we can have multiple LANs on a given switch. Back in the old days, a router or a hub or a simple bridge would have just a single broadcast domain on it. Or if you sent out an ARP, it would go across all ports, that kind of thing. Bomb traffic would get sent to every port, and it would be just one network. With the advent of ISLs in Cisco, and then eventually 802.1q, which is the public version of that, or the non-proprietary standard of that, and VLANs, we're able to do VLANs, and we have multiple virtual LANs on a given switch. So that's not what a bridge domain is. So a bridge domain is a collection of one or more subnets. So we can assign a subnet to a bridge domain. We're going to put ANPs inside of them, application network profiles in them. We can, in fact, an ANP could span multiple bridge domains. It can span multiple switch nodes, and MAC addresses must be unique within a bridge domain, but they can be identical outside of a bridge domain. When we create a bridge domain, give it a name, we're going to associate it to a given VRF. If you do not associate it to a VRF, it will not work. Endpoint retention, we can do DHCP relay, monitoring, forwarding control, etc. So what do we do if we don't have a layer 3 header? ACI Fabric is host routed, so that means we forward packets based on their /32 if it's IPv4, and the host route for IPv6. But if the packet is a layer 2 packet and there's no IP header in there, if by default, if we know the destination MAC address, we know where it is, we know where to send it, we send it to the egress leaf, and then we look up the location, we route it to the egress leaf. If we do not know where the layer 2, if we don't have any idea where to send it to, then we have two options. So the layer 2 unknown unicast. So the Ethernet frame is, we don't know where to send it, or the ingress leaf doesn't know where to send it. It can send it up to the spine, and if it does not know where to send it, then it will drop it. If it does know where to send it, of course, it will send it to the appropriate egress leaf. The other option is if we don't know where to send it, then we'll flood it to all ports or all endpoints in a given bridge domain. And that mimics traditional flooding behavior. If you might want to do that, or you typically will do that in the cases where we're not using the Anycast default gateway. So we're not using pervasive SVI on the leafs. Maybe our default gateway is we're transitioning from a 7K, and the default gateway is still in the 7K, or maybe the default gateway is on a firewall or load balancer. In layer 2 unknown unicast, we can either flood it or we can do an optimized flood. And then for ARP, defaults to layer 3 unicast. So if we do an ARP request and we know where the actual destination, or we know where to send the ARP, we'll send it to the egress leaf, or we can also just set it into flood into the entire bridge domain, which mimics traditional ARP behavior. All right, now let's talk about subnets. In ACI, each subnet is a child of a bridge domain. So just like on a On a traditional networking environment, we'll have a VLAN, and then we can attach an SVI to that VLAN. Same thing is true for a bridge domain. A subnet we can attach to a bridge domain. A bridge domain may have more than one subnet, just like in an SVI. You can have multiple networks on a given SVI. You can have multiple subnets on a given bridge domain. Subnets must have a unique IP address within their context. So subnets must have a unique IP address range in a given context. You can overlap IP space as long as they're in different contexts. Now, context, I've used the term before. I believe context, also VRF, also private network. Private network, VRF, and context are all interchangeable in ACI. So if I use one of those terms, I mean the other ones as well. So I can have 10.10.10.10.0/24. I can have it in Coke's context. I can have it in Pepsi's context. If I'm Pepsi and I have Pepsi and I have Mountain Dew, which are two different beverages that they sell, then I can have a context Pepsi and a context Mountain Dew, and I can have 10.10.10 in both of those. So as long as they're in different contexts or different VRFs, we can overlap them. But in the same VRF, they must be unique. Subnets can span multiple EPGs, and they typically will. And subnets automatically create SVIs on leafs where endpoints appear. So this is a pervasive default gateway. So if I have, for example here, let's just draw a really quick and dirty ACI fabric. Right, 2 spines and 2 leaves. If I have a device, this could be a VM or it could be a physical host that's plugged into this leaf, my default gateway is going to exist on leaf number 1. For a host over here plugged into this leaf, my default gateway is going to exist on leaf number 2, even though they're the same IP address. That's because we have a pervasive default or anycast gateway. So our default gateway exists in whatever leaf that we have endpoints attached. So to create a subnet, we go into our tenant. Here we have tenant 5.6. We go into networking. We go under the bridge domain. So we've created a bridge domain called VM data. And then we go into subnets. We right click and we add a new subnet. Gateway IP address, that'll be the SVI or equivalent to the SVI. We'll give it an IP address and a mask. We can do a private to VRF, so this is going to be scoped only within the tenant. It's not going to be advertised externally outside of the ACI fabric through a routing protocol. Or we can do advertise externally, which we will scope it to the external layer 3, to the L3 out, and we can advertise it out on one of various protocols or multiple protocols, routing protocols if we wanted to. And then we have this third option here, which is shared between VRFs. So whether I pick private to VRF or I pick advertise it externally, in addition, I have the option of shared between VRFs. And that allows me to do essentially the equivalent of VRF route leaking. So I can provide access to the subnet to a different context, a different VRF within the same tenant, or I can provide access to a different tenant on their VRF. I can treat this as a virtual IP address and make this IP address primary. So this is if I'm going to do something like common pervasive gateways. So in a later section, a little bit more advanced section, we're going to talk about how we can do things like dual fabrics. So I can have a fabric in one location and a separate independent ACI fabric in a different location. I can put a layer 2 connection between them, either through just dark fiber or some sort of link or a DCI like OTV. And I want to provide VM mobility. So I want to be able to vMotion from one fabric to the other fabric. Well, I have that pervasive default gateway. I can do what's called a common pervasive default gateway. I can have the same SVI, same default gateway on multiple fabrics and share them without doing IP conflicts. So that's what I would set up here. I can also do neighbor discovery under subnet control. I can do neighbor discovery for IPv6, and I can do query or IP if I want to do IGMP snooping on that given network. I can pick an L3 out, so that'll associate the subnet if I want to be able to make this subnet available to an outside routing protocol. I can also pick a route profile if I want to be specific about those routing protocols. Now let's talk about endpoint groups. So an endpoint group is a logical entity containing a collection of endpoints with common policy requirements. So common policy requirements might be security, might be QoS, might be access to layer 4 through 7 services or redirection through layer 4 through 7 services. Endpoints are the individual units of this endpoint group. So these could be virtual machines, these could be physical servers, they can even be containers. So it can contain physical or virtual. They'll have an address, location, and whatever attributes. So it could be an external router, it could be a layer 2 connection, such as a VLAN, it could be an individual host, it could be a port group on a hypervisor, or it could be a VM. So policy and security enforcement occurs at the EPG level. This is something that we do to save on hardware forwarding table space, ACL space, etc. So we're going to apply security profiles to the EPG rather than to the individual hosts. So in this case, we might have a one-to-one relationship. So whatever security profiles we have for this EPG, we only have one device in that EPG. It's going to be a one-to-one mapping there. But for the web EPG here, we have multiple hosts inside of that. And we can, if we add a host into that EPG, it automatically inherits whatever security profiles, whatever forwarding profiles, whatever QoS, etc. that we have defined for that EPG. An EPG can span more than one network, more than one subnet. By default, all traffic within hosts inside of an EPG is allowed. So there's no restriction. And by default, all traffic into an EPG is disallowed, and all traffic out of an EPG is similarly disallowed unless we specifically allow it. So this is whitelist networking. We do have the ability to not enforce so that we can let everything talk to everything else, although that's not generally a recommended path. We also have the ability, if you need to, we can also disallow intra EPG communication. So it's basically like an isolated private VLAN. So if that's enabled, then these two VMs, even though they're in the same EPG, even though they're on the same subnet perhaps, they will not be able to communicate with each other. So how do we define an endpoint group? The two most common ways that we define an endpoint group is through a VLAN and also through a VMware like port group. So if we have a virtual, we have ESXi, for example. So this is probably the most common way, so I'll use that as an example. In ESXi, we're going to have a port group, and that port group is going to be assigned to a VLAN externally, and that's going to plug into an ACI leaf. So we have our VM here. We attach that VM to a port group so that the frames that leave this virtual machine, the packets that leave that virtual machine, are going to get tagged with an 802.1q header. So they'll enter the leaf with a VLAN 10 tag on top of that. And that's how we can mark an EPG. A different port group, so this is let's say this is our web port group here. A different port group, such as our app port group, and we will attach a VM to that. We'll have a different VLAN, so that'll be VLAN 11. Now, these can both exist on the same subnet, so this is a lot like private VLANs. They can both exist on the same subnet, but we're going to enforce policy between the web port group and the application port group, between the VMs and the web group port group and the VMs and the application port group. We're going to enforce it through ACI and prevent whatever traffic we want to have. We're going to prevent all traffic except for the traffic that we explicitly allow. So that's how commonly we do that. Now, something to keep in mind in terms of VLANs, what's the scope of VLANs? Well, typically if we're going to do this, if we're going to only have a couple of VMs in a given port group, so we're going to have a lot of port groups. We're only going to have a couple of VMs in a given port group. What happens to the number of VLANs that we use? Traditionally, in traditional networking, we're limited to 4,000 VLANs because VLANs are scoped to an entire network or entire set of switches. In ACI, we can actually scope our VLANs. We can make their significance down to the port. So if I have a different port over here, and I have a different device for a different tenant, or even on the same tenant perhaps, plugged into that port, and that host is plugged into VLAN 10, this VLAN 10 can be a different scope than this VLAN 10. So they're actually two different VLANs, even though they're both called VLAN 10. So I can do per port VLAN scoping. So that'll get us to well beyond 4,000 VLANs. But let's clear that out. So there's different ways that we can identify endpoint groups. So VLAN, we can do a physical port. We can also do VM attributes. We can do virtual ports. We can do VXLAN and NVGRE. We can even signify an endpoint group by IP address. Normally we do it by some sort of segmentation, but we can also do it by IP address if we have the -E models of the leafs. So that would be the 6-port gem module on the 9696 or the 96128, or the 93, 96, 93, 128, or the 93, what is it, the 9372-E's. So that's the PX and TX. If they have the -E, then we can do IP address based EPGs. Also, if it's the EX, so that's the 93.180 and the 93.108, we can do, or 106, or we can do IP based endpoint groups. In the future, we'll be able to do things like subnet, L4 ports, application, or whatever. So those are potential future endpoint classifications. So applying policy to endpoints. In ACI, when we talk about an endpoint, that's a VM or a physical server. So how do we push the policy? So we have two different places to push policy. One is to push the policy to the node. So a node is a leaf here. The APIC will push the policy to the node, and then the node will push the policy into the ASIC, into the forwarding tables. Now, forwarding tables in networking are like TCAMs or CAMs, are a very limited resource. The reason why we use, so CAM memory and TCAM memory, these are valuable resources, and there's a limited amount of them, depending on the chip. And different chips have different amounts of them, so different models may have different amounts per leaf, etc. But it's a precious resource, and we want to conserve it as much as we can in order to get as much policy as we can throughout the entire fabric. So one of the things that we can do is we can restrict. Just because we know about an endpoint doesn't mean we have to publish the policy for that endpoint or that endpoint group into a given node. If you're familiar with the Nexus 7Ks, they do VLAN pruning. So if a line card does not have any ports associated with, say, VLAN 100, then the CAM and TCAM entries for VLAN 100 are not programmed into that line card, allowing that line card to preserve its TCAM space. So it is TCAM and CAM. So this is a specific type of memory. So when a packet or a frame enters in an interface, we have to do a lookup. We have to do a layer 2 lookup, or we have to do a layer 3 lookup, or we have to do a layer 3 LPM, longest prefix match. What the TCAM and CAM memory allows us to do is we can search an entire table in a single clock cycle. So if you think about it, that's what we want to do. As a packet comes in, so this is a packet. It could be a layer 2, it could be a layer 2 frame, or it could be a layer 3 packet. As it comes into an interface, we need to look at the header and determine what to do with it. And we should be able to determine what to do with it before the next packet comes in. If we don't know what to do with it before the next packet comes in, that means we got to buffer it, and we're going to be behind the curve. We're going to be behind the power curve there. So what we want to do is we want to stay ahead of our workload. We stay ahead of our evaluation. So we use our packet or frame evaluation. So we use what's called TCAM or CAM, content addressable memory, or ternary content addressable memory, or something like that. There's basically forwarding table. So what we do is we can search the entire, it might be 10,000 entries. If you have like a little Netgear switch at home that probably has about 2,000 entries or 8,000 entries in its CAM table, So we can search all 8,000 entries if we even have 8,000 entries. We can, no matter whether or not we have 2 entries or we have 10 entries or 10,000 entries, we can search all of those entries for a match in a single clock cycle. With TCAM, we can search for a longest prefix match, which is what we need in routing. We can search all of our routing entries, our FIBs, forwarding information base. We can search that all in a single clock cycle. Things like DRAM, SRAM, we can do a lot. We can have a lot more memory, and we can have much lower power. So TCAM and CAM memory are kind of power hungry, but we can't search it in a clock cycle. And if we have a lot of memory, we might get behind the curve. So it's more expensive and it uses up more power. So that's why, whether it's Cisco or any of the other vendors, the forwarding table space is at a premium. So one of the things we want to do is limit, if we have EPGs, for example, so we have this source EPG on this leaf and on this leaf, and we have the destination EPG on this leaf and this leaf. These guys don't need to know the information because they don't have any members of that EPG, so they don't need to be programmed with that information. Also, we have 2 different steps of a given policy. So we define the policy as users, as administrators, into the APIC controller cluster. Then the APIC controller cluster will need to, in order to use this policy, push the policy into the local leaf, into the local node. That means putting it basically into its SSD and into its control plane. And then it will need to push it into the ASIC. So those are 2 steps. So policy push and policy programming, those are 2 separate things. And we can do on demand, we can do immediate, and we can do pre-provisioning for pushing our policy. If we do on demand, policies are only pushed to a leaf node upon the physical NIC attachment and VNIC association with the port group. So if we have, as soon as we discover an ESXi host, so here's an ESXi host. As soon as we discover that we've attached a physical NIC, so VMware calls it a VM NIC, or PNIC is another name for it, and the VNIC association, so the VNIC associated with the port group on the vSwitch, then we will push the policy to the leaf. That's on demand. Immediate, policy push to leaf upon hypervisor PNIC attachment, and the LDP or OpFlex resolves hypervisor leaf node attachment. So that's even before so that means the VM hasn't even powered up, or we haven't done a vMotion. Maybe we've got a port group here, but there's no VM on that ESXi host yet because we haven't vMotion there. So if we do immediate, as soon as we apply the policy in the APIC, it'll get pushed down to any leaf that already has a hypervisor that is attached to that leaf. So it's kind of pre-pushing that policy. We can also do pre-provision. So that's the policy is downloaded to a leaf regardless of CDP or LDP neighborship, even without a host connected to that VMM switch. So that just pushes it no matter what. Policy programming in leaf node hardware based on deployment immediacy. So that's programmed into the actual TCAM space or ACL space, depending on what it is. On demand, policy is programmed into policy cam only when reachability is learned through the data path. So that's on demand. And immediate means policies are programmed into policy cam once received by the APIC as defined by the resolution immediacy policy. So that means if we have a policy, don't wait for a VM to show up. Go ahead and push it into the ASIC, even if there's no VM attached yet. So we can pre-provision, or we can do immediate, we can do it on demand, or also we can do pre-provision. So if we do immediate or if we do pre-provision, then that means immediately we're going to push that policy from the policy engine on the leaf into the actual ASIC and for hardware programming. Now, why would you want to do one versus the other? If you have a smaller fabric, you might as well do immediate because typically for smaller fabrics, we're not going to run into the limit in terms of cam space or TCAM space. But if we want to be careful, if we want to really stretch out the amount of cam space that we have, the amount of forwarding table space we have, we can do it on demand. either way, it's probably gonna work, and not probably. Either way, it's gonna work. So depends on whether or not you want to conserve that forwarding table space or you're not concerned about that forwarding table space. The leaves, depending on the model, will have hundreds of thousands of entries potentially for forwarding space for layer 2, layer 3 entries, and for LPMs, longest prefix match. So for smaller numbers of endpoints, it really doesn't matter. But as you start getting up there, you might want to be more concerned. So policy table size reduction, one of the ways that we can conserve forwarding table space is that we can do policy table reduction size. So if we have, in traditional networking, we have 5 endpoints. So these are VMs or physical hosts. They have 5 sets of IP addresses, 5 sets of MAC addresses, etc. And we do filters, and then we have 4 different destinations. So 5 times 4, 5 times 5 times 4. So we have 5 filters, we have 5 sources, and we have 5 destinations. 5 times 5 is 25. 25 times 4 is 100. So this is going to require 100 policy entries. That means 100 entries in our forwarding table space, in our ACLs or whatever, or in our CAM tables, TCAM, forwarding tables, whatever. We're going to require 100 entries out of that. With ACI, we're going to group everything into a single EPG. So our list is going to contain, we're going to only put in 1 rule. We've got 5 filters that require 5 rules. And we've got 1 destination. So basically, we only have to do 5 entries into our TCAM space, into our ACL space, because we have 1 source going to 5 different filters, and all of those go to 1 single destination. So that's why we use EPGs. EPGs are security group tags, or like security group tags. And what that allows us to do is preserve space. This tag, so the EPG, is in the VXLAN header. So a bridge domain is a VXLAN, but inside of that VXLAN header is also the source the source EPG. So we can actually build policies based on the source EPG rather than the addresses that are located within that EPG, and that just allows us to preserve forwarding table space. All right, now let's talk about application network profiles and contracts. So defining some terms here. So an ANP, an application network profile, are a group of EPGs and the contracts that define the communications between them. Typically, that's going to encompass an application and defines our policy and communication for that given application. A contract is a policy definition, and it defines how EPGs communicate with other EPGs. Remember, by default, ACI is a whitelist networking environment. So if we want an EPG to talk to another EPG, whether that's an internal EPG, something located inside of the fabric, or an L3 out, or an external EPG, something located outside of the fabric, we have to have a contract to allow that traffic to allow through. So contracts are a group of subjects, and a subject contains filter, action, and label. And a contract contains 1 or more subjects, and that's the relationship between those. So an ANP defines which EPGs can communicate and how they communicate. We use a provider-consumer relationship. So we're going to take a contract, and we're going to let's clear that out here. So let's take a contract. This contract, so the web farm is going to provide this contract, and the users are going to consume the contract. So this is a one-way contract. Now, the direction of provider and consumer is pointing towards the users, but the direction of traffic, of course, is this way. So we're going to provide a contract that allows port 80, perhaps, into the web farm. Now, can the users talk to the app servers? Can the users talk to the database servers? Even if it's on a publicly routable subnet, no, they can't, because we don't have a contract. So users consume the web contract. We can have a two-way contract. Web and app provide and consume services between each other. So we have provide and consume and provide and consume. And then here we have a one-way contract. The database layer provides service, such as over 3306 TCP, to the app servers. Now, just because we're providing 3306 doesn't mean that the users can come in on 3306. That will not be allowed because the contract is provided by the database farm and is consumed only by the app server. If we wanted to allow that, we could do another contract. Now, this would not be a good idea typically, but just to show we could do it, we could provide that same contract to the users, and the arrow would actually be that way. You can tell that arrow there. So how do we create a contract? Well, contracts are groups of subjects which define communication between the source and destination EPGs. Subjects are a combination of a filter, an action, and a label. So every subject is going to have a single, we can do more than one filter, although typically we're just going to do one. We're going to have an action, such as permit. There's a couple other ones we can do too. And then we can do a label. We'll just call it web access is port 80, of course. And then we can have multiple subjects. Current policy options that are supported are permit traffic. We can deny or block traffic. That's if we're doing taboo contracts. If we're doing unenforced, if we're just letting everything talk to everything else, then we can put in these taboo contracts to block certain types of traffic. We can redirect traffic, have it go through layer 4 through 7 device, such as a firewall or load balancer. And we can mark traffic, such as assigning it to a cause lane or do DSCP marking. Future options, actually, they're supported in 2.0, depending on the type of leaf you have, is we can copy and log traffic. So shared services. So we can provide shared services throughout all tenants. So what we can do is we can provide a contract that we can share out. So we can share a contract so that our app servers can consume things like DNS and DHCP. And these can be on a different tenant over here. They can be in a different tenant, and they can even be in a different, or they can be in a different VRF, certainly within the same tenant, and they can also be on a different tenant. Endpoint groups. Endpoint groups are a logical entity containing a collection of endpoints with common policy requirements. Typically, often cases, an EPG will represent a tier in an application. So the web tier, application tier, database tier, etc. So endpoints can be directly or indirectly connected to the fabric. So we could have a host that just plugged directly into a leaf. We can have a hypervisor that's plugged directly into a leaf. We can have a hypervisor that is plugged into, say, a Nexus 5000. And that 5000 is plugged into a leaf. Often in case we'll see that when we're doing things like migration from a legacy architecture to the new ACI architecture. Our endpoints can be virtual, they can be physical. They have an address, an identity, a location, and attributes. So that's what our endpoints are. Typically, right now in ACI, an endpoint group is represented by a VLAN. So in a hypervisor, a VM will be part of a port group if it's VMware, and it oftentimes is VMware. And that port group will be assigned externally through a VLAN. So we can assign a VLAN to a given EPG so that when that VLAN enters that leaf, whatever hosts are in that port group and thus whatever hosts are in that VLAN are going to be part of that EPG. So policy enforcement and mapping. Policy and security enforcement occurs at the EPG level, not at the endpoint level. So we're going to build security rules based on an EPG. That means that if we have a single host, if we need to do security based on an individual host, then we just put a individual host inside of an EPG. So we just do a one-to-one mapping. Host equals an EPG. But typically, we're not going to need to do security based on an individual host. We're going to do security based on our virtual machines, multiple devices that are related to each other. So if we have multiple virtual machines, or that might be multiple web servers in a given application tier, they're all going to be treated the same, so we can apply the same security policy to all of them. So the security policy will then, the scope of that security policy will be that EPG. So right now, we typically will identify an endpoint group by a VLAN. And if that's a physical network, so it's a physical network. If that's a physical host, like a bare metal host, that'll just be an 802.1q port, 802.1q VLAN up into a leaf, or up into something like a 5K and then up into a leaf. It can be just a physical port. So if I plug a host directly into a leaf and I'm just sending raw Ethernet frames, then I can do that. I can do VM attributes. I can do virtual ports. I can do VXLAN and NVGRE, so external VNI segments. I can do IP address, so I can make an endpoint group based on IP address if I'm doing 1.2, and a switch that has the -E, so that's or the -EX. So those are host-based endpoint groups. Future, we can do things based on subnet, by a layer 4 ports, by application, and by whatever mechanism that we want. Policy contract actions. So currently, the policy options that are supported is that we can allow traffic, permit traffic. So that's part of the whitelist networking in ACI by default, is that we're going to block all inter EPG traffic. So from one EPG to the other, we're going to block all traffic. If we're doing a taboo contract, we can deny traffic. We can redirect traffic, such as to an L4 through L7 service, such as a load balancer or firewall. We can mark traffic, set DSCP labels, cause labels, etc. And in ACI 2.0, the Congo release, we also support copy traffic and log traffic. Now, these are only supported in the 9300-EX hardware. So that's the 93180 and the 93108, I believe, or 106. I can't remember which one it is. So why copy? Especially when we have span ports, span ports copy all traffic. Copy in the contract is only going to copy pieces of data that match that rule, and the same thing for log. So whatever, if we have a hit, if we have a miss, we can log that information, and we can use that, especially if we have things like applications that we're not sure how they talk to each other. We can log whatever hits or misses that we have and try to figure that out there. Shared services. So one of the things that we might want to do is provide, if you're maintaining an ACI fabric or maintaining a network fabric, we might want to have some shared services between all of your tenants. So things like DNS, things like a DNS, a DHCP server, maybe an NTP server, maybe a backup service, iSCSI, storage array or something like that, NFS storage array. We may want to put that in, may want to have a common tenant. We can put that into the common tenant, and we can share those services across all of our tenants, and we can do that through providing those contracts. Now, whatever subnet we have the app servers in and the web farm in, we just make sure that we do that as a shared subnet, and the same thing here in the common tenant. And then as soon as we provide some contracts, and as soon as we consume this AD contract, so we created this contract here that's allowing the traffic through, as soon as we set the app server EPG and the web farm EPG, no matter what tenant it is, as long as we've marked the subnets as shared. The minute the moment rather that we consume this contract, the VRF route leaking is automatically applied, so we don't have to do anything above that, beyond that. And so it doesn't matter. It could be the common tenant, it could be a whatever tenant, as long as the subnets are set to share that subnet. Even if it's a non-advertised subnet or it's an advertised subnet to the outside world, it doesn't matter. It doesn't matter if we're in one context and we're from one tenant and we're doing from one context to a different context in the same tenant, or we're providing a service to multiple tenants and multiple contacts. As long as we have those subnets marked as shared, and as long as we provide that contract and then consume that contract, the VRF route leaking is set up automatically. So we do have taboo contracts. So most of the time in ACI, when we set up ACI's whitelist, so that means that inter-EPG communication is disallowed by default. We have to create contracts. So we have app services and web services here. We have to create those contracts, and then in order to do an explicit allow. We can apply a taboo contract on top of that. And taboo contracts are things we do not want to allow, and they will override whatever services or whatever subjects that we have and whatever filters that we have in place. So for example, we have an outside world here. So that's the internet. Using the web services contract, maybe this is port 80, maybe this is port 443. For whatever reason, we don't want to allow port 80, so we apply that contract here. And even though that web services contract provides port 80, the taboo contract overrules it, and we're not allowing port 80. So you can use that to apply specific disallow rules. I'm going to skip this one entirely. So when we create a contract, we can scope that contract. Here we create a contract. The scope is either going to be scoping. It's only going to be visible to the application profile. It can be visible to the VRF, to whatever context we have. It can be global, or it can be tenant. So if it's tenant, then whatever context we're in, or whatever VRF rather. There's VRFs and contexts are the same thing. Or global means we can provide this contract to any tenant inside of the ACI fabric. If we're going to provide a contract to any tenant or any VRF, we need to make sure that we do shared between VRFs. Now, it doesn't matter if the VRF is in the same tenant or in a different tenant. So a tenant can have multiple VRFs. Coke and Pepsi can have multiple VRFs. For example, Coke can have Coke, Diet Coke, Sprite. Pepsi can have Pepsi, Diet Pepsi, Mountain Dew. Doesn't matter, as long as we do shared between VRFs, we can provide those contracts and make them available to other VRFs, even at other tenants. For EPG communication in the same tenant, contracts are created and a tenant are available only by any VRF EPG in the tenant. However, they are still governed by the contract scope rules. EPG to EPG within a VRF require a minimum of a single consume-provide relationship. All routing is already established in the VRF. I'm just going to skip this one too. All right, now let's talk about ACI quality of service real quick. So the overall QoS process flow, our traffic classification and marking is done on the ingress leaf, and that's it. We don't do any classification or marking on the spine, and we don't do it on the egress leaf. So it's all done on the ingress leaf. Buffering and queuing is done on the ingress leaf. It's also done on the spine if we're going through the spine, and done on the egress leaf as well. In ACI, there are 3 user configurable classes of service: level 1, level 2, and level 3. Level 3 is the default. If you do not do anything, everything gets put into the level 3. The classification options, we do it in the contract. It can be done on DSCP or .1p, so that's the cause lanes, and via the EPG. Marking, we can do DSCP marking. Queuing and scheduling, we have strict priority queuing available or deficit weighted round robin. The class ID is carried in the .1p of the VXLAN outer header, and no reclassification is allowed on the spine or the egress leaf. You can set the QoS policy in a contract. So here we've got 2 EPGs, server and storage, and we've got a contract between them that is setting our QoS. All traffic between EPG1 and EPG2, or all traffic between server and storage EPG here in this example, is set to level 1. So we've set that down to level 1. So you can set priority for all traffic between 2 EPGs. You can also do a custom QoS applied at the EPG level. So this is EPG storage here. You can match on DSCP or .1 priority. Here we've set a custom QoS. We're doing AF31 to AF33, we're setting that to level 2 priority, and AF41 to AF43, we're going to set match on those DSCP values, and we'll set a 2 priority level 1. The DSCP takes precedence over .1p, and the same policy supports DSCP mark. No custom QoS is enabled. Traffic for the EPG is assigned to the class service based on QoS class. In this case, we're setting it to class 1. If you don't set anything, it will be assigned to level 3. And now let's take a look at the application network profile again, just to review. An AMP is a collection of EPGs and the contracts that govern their communication. So here we've got a layer 3 context, so this is a VRF. Under that layer 3 context, we have multiple bridge domains, 1 bridge domain per level. So we've got our web tier, we've got our app tier, we've got our database tier. We've got several EPGs. So 1 bridge domain to 1 EPG, 1 bridge domain to 1 EPG, 1 bridge domain to 1 EPG. Endpoints are inside of that EPG, and we've got a variety of contracts. We've also got these outside EPGs. So these are 2 external L3 EPGs, and they are represented by longest prefix match here. So we've got 0/0. We have a much more specific match. This is 10.19.21 0/24, so a class C. We have the contracts. The web contract is being provided from the web EPG to the outside world. So this would be probably 443 or port 80. We've got a Java contract being provided to the web tier so that, for example, the outside world can make communication to the web EPG, but it cannot to the application EPG because we don't have a contract providing that consumption. So the Java contract is provided can be consumed by the web, so maybe that's port 8080. And the SQL contract is being provided on the DB EPG and is being consumed by the app EPG. We've also got a contract here, the dev contract. So this is being provided by all 3 tiers, and it's being consumed by the dev EPG. So these are our developers, perhaps. And we might be doing things like port 22 for SSH or remote terminal server, something like that. We can also have a remote EPG route leak it from perhaps the common tenant. So this is a service EPG, and we've got DNS filter, Active Directory filter, and these are all being consumed by the web, app, and database EPG. So again, let's take a look at our logical So again, let's take a look at our logical model again. We have the root or universe, and then we've got a tenant. Underneath of a tenant, we're going to create application network profiles. We're going to create EPGs under the ANPs, at least one. We'll also have a bridge domain, and the bridge domain will have a subnet. So this will be our Anycast gateway or SVI. This will exist underneath a VRF, and we'll have multiple VRFs, or we'll have at least one VRF for a tenant. We can have multiple. We're going to map our EPGs to VMM or physical domains. Typically in VMware, typically we're mapping a port group to a VLAN. We've got VLAN pools assigned to that VMM domain. We're attached them to an attachable entity profile. We've got interface policy group and policy. So policies are grouped together into an interface policy group. We select our interfaces, and then we select the leaf switches.